GATE 2021 Metallurgy paper, question 34. For a fully developed one-dimensional flow of a Newtonian fluid through a horizontal pipe of radius r, the axial velocity is given by this expression delta p upon L r square minus r square upon 4 mu, where delta p represents the pressure difference P1 minus P2, mu represents the dynamic viscosity, r is the radial distance from the axis, and L is the length of the tube. And we are supposed to find the shear stress exerted by the fluid on the tube wall. Okay. So since it is a Newtonian fluid, and we are required to find the shear stress, so the Newtonian law of viscosity comes into play. So according to Newton's law of viscosity, it is nothing but mu dV by dy, where mu represents the shear stress, mu is dynamic viscosity, dV by dy represents rate of shear deformation. So we will be using this expression to find the shear stress exerted by the fluid on the tube wall. Since we are interested in tube wall, so it means we are interested at R equal to capital R, because shear stress will change in the radial direction and we are required to find the shear stress on the tube wall. So in radial direction, R should be equal to capital R. Okay. Now, so using the Newton's law of viscosity, I will use tau is nothing but dV by dy. Now here, what is y? Y is in this direction. Okay. Now from the figure, you can clearly see that y plus r represents capital R. Okay. If this is the central axis, okay, so y plus r will be capital R. Likewise, if you differentiate both sides, dy will be nothing but minus d r, because capital R is constant, so its differentiation will be 0. So I can express the Newton's law of viscosity in terms of radius, mu dV by dr with the negative sign due to this. Here the negative sign. Now all we have to do is we have to differentiate the velocity, that is the axial velocity in z direction, with respect to r. Okay, where Vz is given to be delta p upon L capital R square minus R square upon 4. So if we have to differentiate the velocity with respect to r, small r, dvz by dr, since delta p by L is constant, so it will come out of the differential. It will be, and 4 mu is also constant, so 1 upon 4 mu will also come out of the differentiation. So d by dr of r square minus small r square. it is nothing but, since capital R is constant, so its differentiation is again going to be 0. So delta P by L, the final expression will be 1 upon 4 mu minus 2R. Okay, that is dVz by dr. But since we are interested in finding the shear stress on the tube wall, so in that case, this R should be equal to capital R. If we apply the boundary condition, the R will be equal to R at tube wall. Okay. So therefore, this expression will become delta P by L 1 upon 4 mu minus 2 times R. Okay. Yes. So further simplifying it, now we will use this expression dV by dr in our Newton's law of viscosity here, okay, which is at R equal to capital R. So tau will be nothing but minus mu, and this is dV by dr at R equal to R, capital R, at the tube wall. It will be delta P by L upon 1 upon 4 mu minus 2R. So the shear stress at tube wall will be nothing but, mu will cancel mu, 2 will take 1 power of 2. Here you will get delta P by L R by 2L. Okay, so that is your final solution. So if you look at the options given, so option A is the correct option, delta P R upon 2L. Okay. And one thing that you must observe here, the velocity in z direction is a function of r square, so it is parabolic in nature. The variation of velocity in axial direction is parabolic in nature. Maximum at the center and 0 at the wall boundaries. Okay, like this. This is V max, and here it is V equal to 0. Because if you put R equal to R, they both will cancel at wall boundary, and Vz will become 0. And if you put R equal to 0, small r equal to 0 at the axis, this will become the maximum. It will maximize. The expression is going to maximize. The same goes for the shear stress also. Since the shear stress is single power of r, so it is a linear variation. It's a linear variation with maximum value at the wall boundaries and minimum value at the axis of the tube, like this. This is shear stress, and this is this is the variation of velocity. Okay, so you can look up the Hagen-Poiseuille's principle. For more details, you can also refer lecture 31 of NPTEL course Fluid Mechanics by Professor S.K. Som, Department of Mechanical Engineering, IIT Kharagpur.